Hello everyone, welcome to RISC Zero workshop. And today we're going to learn about general purpose zkVM, then about Bonsai, zk proving service, and then we'll finish with zkCoprocessor. This is our proving service that allow easy off-chain zk proof generation with on-chain verification. So let's get started. So what we'll cover today, we'll go over first with the zkVM architecture, then terminology, then we'll go about features, what make RISC Zero stand out across other zk products. We quickly go over example to show you how easy it is to get started and run and generate zk proofs on RISC Zero. And then we go over zkCoprocessor. We'll see how seamlessly you can integrate Bonsai within your Ethereum application. So zkCoprocessor is very important because zkVM and Bonsai together can act as a coprocessor to the smart contract application. So, and this unlocks quite a lot of powerful new applications on Ethereum. So you can offload computationally intensive functions to zkVM and then get back a very small zk proof that you can verify on chain. So RISC Zero was started in 2021 and is focused on revolutionizing the internet by creating the infrastructure and tooling necessary for Web3 developers around the globe to build zero-knowledge software. We are bringing general-purpose computing to the zero-knowledge ecosystem, enabling users to trust programs run anywhere while allowing developers to use the tools they already know and love. So we made a circuit that usually developers have to construct to generate their zk proofs and actual VM. Circuit doesn't change from program to program, it stays the same, but you have two inputs that you have to send to your circuit. It's a program that you want to generate a zk proof on and input data. And then a circuit will take these two inputs and generate zk proof for you. Circuits is within a zk VM, so it's part of VM. Let's look at zkVM, very high-level overview. And let's start with the normal VMs, virtual machines that we all know. How the architecture of them is very similar. You run VM on some type of host, and you send a program that you want to run on zkVM, and the input data that you want to run this program on. And virtual machine takes these two inputs, generates it, and provides you with some output of your program. With the zkVM, we have a very similar architecture. You run zkVM on the host, and then it takes two inputs, a program that you want to generate a zero-knowledge proof of, and input data for this program. And the zkVM run this program, generates output of this program, and on top of it, it also generates a proof that corresponds to this program and to this input data. And all of this data is part of the receipt, and we'll learn just in a minute what the receipt is. But this is a definition of verifiable computation, where you just show someone a proof, and this proof verifies that you run some program with some private data, and that's it. So RISC Zero zkVM implements RISC-V standard open source microarchitecture. And why we implemented a circuit that implements RISC-V microarchitecture, microprocessor? So advantages of that instead of making our own domain-specific language that's difficult to learn, usually difficult to learn for the users, or writing our own compiler, our users can write their programs that they want to generate a proof of on any languages that LLVM or GCC compilers support. First, we start focus on Rust to make sure that we provide the best idiomatic developer experience for our users, and then we extend to other languages. And there is also zkSNARKs. So this part is a bit advanced, so if you're new to zk to zero knowledge, it's okay if you don't understand. So we use zkProof to generate proofs in parallel. So our RISC-V circuit generates zkProofs. And then we use recursive circuits to recursively aggregate many proofs together into one SNARK. And then we use Groth16 circuit to convert zkProof into SNARK. What it does, it provides you with a very tiny proof, SNARK proof, that you can verify on chain. So RISC-0 zkProof is Groth16 SNARK, which is quite exciting. So let's go a little bit deeper inside the KVM architecture, but still have like high-level architecture. So Rust compiler takes Rust code and generates object for LLVM. LLVM generates a bytecode, and it also generates this RISC-V binary. And this RISC-V binary is the input for the KVM. Executor takes this binary and generates execution trace or session. And then prover takes this execution trace, checks its validity, and then generates a proof, which is inside the receipt that will go in a minute. So right now, you can have 256 megabytes of data inside the KVM. So why it's important, and what can you do? So developers can run Rust code inside the KVM, and proof execution was done correctly. And the second, the KVM makes verifiable computation easy to get started with. So let's go quickly about terminology. Terminology of the KVM is very similar to, almost identical to virtual machine terminology. So you have a guest, which is a program that you want to generate a proof of. This program that you send as an input to the KVM. Then you run the KVM on the host. And the host is in charge of the KVM. And portion of the KVM that actually generates the proofs, the circuit, we call it prover. So we have guest program that you want to generate proof on. You have host, where you run your zkVM on. And the prover is a part of the zkVM that actually generates Groth16 SNARKs. So receipt, that object that you get from the KVM, it provides you with a valid execution of a guest program. And it also contains two objects inside. It contains journal, public output of a guest, and a seal. Seal is basically Groth16 SNARK, basically a zk proof of correct execution of the guest program that you wanted to, that you passed to the KVM. So now let's look again at the KVM architecture. So now you can see that we pass Rust code that we pass to the KVM is a guest code. And then the KVM runs inside the host. And this is the prover. This is that part that generates our zk SNARKs. And the receipt. Receipt is the object that you get that contains zkProof and public output from your guest program. So now we go to exciting part, continuations. And this is what differentiates RISC-0 from other zk solutions available on the market. We have continuations. So continuations enables you to generate proofs on parallel clusters. On other solutions, you can generate on one CPU. With the RISC-0 zkVM, you can run your proofs on parallel clusters. This is very exciting. So before continuations came around, there was a limit how large your program was. So that you sent to zkVM, how large was your guest program, and it was around 16 million cycles. And after the continuations, the largest proof program that we sent was 10 billion cycles, but theoretically ran to trillions. So it's very large, and it's very exciting. So this means that RISC-0 zkVM allows you to generate zk proofs of very, very large programs, and also it runs very fast. So another part, proof composition. Proof composition makes it possible to verify proofs inside the proofs. So using proof composition, you can create a proof that attests anything to anything that has previously been proven. So here you see that you have output, you run zkVM that generates receipt, and this zk SNARK, growth 16 SNARK, can be program inputs for next zkVM. So it allows you to generate proofs over proofs, which is, again, super exciting. So let's go through a very basic example to show you how easy it is to get started with zkVM. So I want to go through an example that I want to prove you that the number, that a number is a composite number. So composite number is opposite of prime number. So I basically means that composite number have at least one divisor that is not one and it's not itself. So from a user perspective, on the left side you have the guest code that actually checks that numbers that we pass are not one, otherwise it's prime number. It multiplies these two numbers and it sends product back to the zkVM. And this is host on the right. So host just like run the zkVM, and is also responsible for sending data to the guest. So let's look a bit closely at what we need to know. First, we need to make sure that we import functionality that interacts with the host environment over here. Then we read the data that was sent to us from the host. Then we do our multiplication, then we do our very, very intensive computations. And then we commit the public output to the journal. So this this output is a product that we want to, our composite number. And this is part of the journal. So on the host side, host is responsible for getting the data. So we just pick two numbers. Then host is responsible for preparing this data and sending it to the guest program before we actually start executing the guest program. So it put this data into guest environment. Then it takes the prover, and it takes the prover to validate guest binary, and it also provides the input data. Prover generates a receipt, and here you can see how you can use how you can extract output from the journal, and this is how you can verify your receipt. This is you can send the receipt to a third party, and third party can verify it easily. So this is QR code for quick start guide. I highly recommend you to scan it to get started. So if I don't want to run on zkVM locally, there is a remote option, and this is Bonsai. Bonsai enables you boundless computation. With Bonsai, instead of generating proof of your own hardware, you request Bonsai to generate it for you. So Bonsai is highly parallelized, highly performant, and horizontally scalable solution, and is based on zkVM proof engine. And this is a very high-level overview of Bonsai, where you can have a guest, which is part of your trustless software or part of smart contract. You request Bonsai to generate a proof. It sends you back a receipt, and receipt contains zkproof and the journal. So this is the most exciting part, zkCoprocessor. So we want to make sure that zero-knowledge proof integration into Ethereum is possible with minimal developer effort. So this is high-level overview of RISC-0 application on Ethereum using Bonsai. So first, the off-chain component of your app, whether it's the app client or a server, sends a proof request to Bonsai. And then Bonsai generates a receipt, and the app publishes the receipt on-chain to your app smart contract. And your smart contract called the RISC-0 verifier contract to prove the validity of this receipt. If it's successful, the journal is trustworthy. So let's look closer around this RISC-0 verifier. The verifier contract has iRISC-0 verifier interface, which provides with two objects, provides with a receipt data structure and verifier method. So iRISC-0 verifier is implemented by RISC-0 growth verifier contract, and this contract is stateless and immutable verifier. So please scan this QR code for the docs for the zkCoprocessor. And if you want to learn more about RISC-0 growth verifier, this contract is deployed on Sefolia, and you can find the address at this link. And you can choose this contract, or you can deploy your own. So lastly, this is a link for RISC-0 information about hackathons, bounties, links to documentation to zkVM, Bonsai, zkCoprocessor, links to Discord, Telegram channels, where to find us during the actual event. All this information is here on this link. Thank you very much, and I'm looking forward to see you all. Thanks.